Hello and welcome to this presentation about extending Kubernetes with AI capabilities. My name is Gustav Rasmussen and I'm joined here on stage by Marius Tanawa, my colleague and team member, our senior platform engineer. I'm the tech lead of our containerization team in Novo Nordisk, research and development. A look at the agenda for this talk. I'll briefly introduce you to the organization, a quick word about how AI is relevant to us, then go into some of the technical foundation with container images and data before handing it over to Marius, who will tell you more about the exciting new Gefion AI supercomputer. It's currently ranked 21st in the whole world on the Global 500 ranking. Marius will go in details with GPU workload schedulation, some challenges we encountered, and different solutions we came up with. In the end, we'll look a bit into the future and then take questions from you. So briefly introducing our organization and how AI is relevant to us. We are a large global pharma country residing in more than 80 countries, over 60,000 people, and mainly supporting a few different therapy areas. We are primarily in diabetes, but also obesity, then other disease areas such as non-alcoholic fatty liver, chronic kidney disease, cardiovascular disease, and also some brain disorders such as Parkinson and Alzheimer's. We also support more rare disorders such as endocrine or hormonal deficiencies, more rare bleeding disorders such as hemophilia. And as IT professionals, we are building the technological platforms to enable the researchers to improve on these therapy areas. We have a global organization, here you see some of our main sites in US, UK, India, China, and our headquarters in Denmark. We have expertise across the entire value chain in knowledge, and several of our sites operate as transformational research units in relation to the global R&D organization. This allows them to make data-driven decisions quickly and focus their efforts on research. We have a matrix organization. Marius and I, we sit in a containerization team circled here in red. We are part of a horizontal cluster, ML and infrastructure. We work together with other horizontal teams, delivering value to different verticals, teams and clusters. If you caught some of the other talks, both yesterday and today, there was one, for example, yesterday by Danish Bank in Vlogs talking a little bit about team topologies. So in that framework, we are an enabling or facilitating team. We are sharpening the axe so the verticals can better chop the wood. Research is often called the Wild West because it's very easy for a researcher to learn about a new tool at a conference and then acquire it, adopt it into their daily work. This, of course, leads to a rapid growth. Here you just see a few examples across different categories of tools and platforms available. A lot of our efforts go into constantly re-evaluating whether or not these tools still add value or if we should discard some, constantly simplifying and consolidating platforms. So if you caught yesterday's ending keynote, there was very elegant comparison between, on one hand, platform engineering, but then also to Dante's Inferno. In this context, we are taking on the role of Kerberos, so the three-headed dog gating the third circle of hell. Well, hopefully avoiding hell by biting and clawing off the unnecessary tools. How does AI fit into all of this? You see on the leftmost figure, this is global data generated with a projection into next year. Vertically, this is in zettabytes, so thousands of exabytes or billion, trillion bytes, nearing a projection of 200 next year. This picture is also true for Novo Nordisk, of course, less in value, but still the exponential growth tendency. At the same time, you have AI, which is highly capable of massive data handling and processing. In the rightmost figure, you see how AI is overtaken best human performance across a number of areas, such as image recognition, reading comprehension, and language understanding. And of course, we want to be part of that journey and adopt it. It's actually a declared must-win battle for a company. There are two broad categories. Of course, it's a spectrum with things in between, but you have, on one hand, very publicly available or citizen AI. We all want to work with things like ChatGPT for text generation or summarization. Things like Copilot to plug into your IDE for supporting your full software development lifecycle, generate or improve code, generate tests, etc. But for research data in particular, it's highly heterogeneous. And due to the nature of this very diverse data, often we actually need very custom or bespoke AI models. This can be, for example, knowledge graphs or things like AlphaFold generating peptide sequences, etc. It is applicable throughout the entire value chain, all the way in the end, how we most efficiently communicate with doctors, or how do we prevent stockouts through either sales uplift or mixed marketing models. It's also applicable in manufacturing, where we have things like image recognition models that can easily detect defects in vials and pull them out early in the process. However, some of the most exciting use cases can be found in the discovery phase. Generative AI can scan enormous amounts of potential targets to find leads with the right attributes, producing a better qualified sample of leads for preclinical and clinical development. There are different projections. Most of them agree that in healthcare, over a 10-year time span, the rapidly growing window of opportunity exists for adopting AI into the workflow. So how do we get there? This is our equation of success. We backtrack always from the business value we want to achieve, starting from a foundation of fair data, so data that is findable, accessible, interoperable, and also reproducible. Then adding the technology on top, state-of-the-art infrastructure, etc., but also working with people with the right mindset to actually adopt AI into their way of working. And then we typically work in fast iteration cycles, hackathons over 2-week periods or such to deliver on this business value. Now we will talk about container images because they are a little bit special when it comes to ML training and inference, because they can often be quite large and sometimes contain data as well. Usually when making data available to models for training on Kubernetes, for example, is done through either init containers or adopting the sidecar pattern, but exciting new alpha features available from Kubernetes version 1.31. It's the read-only volumes, so OCI-compliant artifacts, basically allowing you to mount data directly into your main container. As we learned yesterday, if you attended Jonas Felix, a very exciting session, Kube Capture, so capture the flag on Kubernetes, we learned how easy it actually is to conduct a supply chain attack where we injected a reverse shell into a public image sitting on Docker Hub. And of course, we want to avoid that. So as we all know, it's a critical component for any containerized application deployment process to have a registry for both container but also model images. We decided to go with Harbor. It's a fully graduated CNCF project. It's both open source and cloud native, and it allows you to easily secure your images. You have multiple potential scanners, accurate trivia as the default. You have things like image signing, federation of identity, and that can help you through role-based access control, ensure you have the same identity as in the rest of your organization. You can connect it to multiple upstreams, daisy chaining or otherwise. We are using it as cache and proxy and connecting it with JFrog's Artifactory. This fits with our global strategy to be software as a service first. If that's not available, we build our own infrastructure on cloud. And if that's not available for some reason, we can build on-premise. You can, of course, abuse data to get it to say pretty much anything you want. This can lead to some rather bizarre outcomes when you use your model for inference. Here's a famous case when asking Google's Gemini model what is the best pizza topping. It suggested glue, Elmer's glue to be specific. And avoiding that requires, of course, a solid data quality foundation. Not only fair data, but you need to have your data also accurate, complete, correct, and unique at the right metadata, tagging, etc. And it is easy for a large company to get its data quite scattered as well globally. So we want to, of course, allow data gravity, data pulling in together other data in related applications and services, because this greatly simplifies data management, security, but also performance. Having data sitting side to side to the models, you get much lower latency for training, for example. So what is the potential end result? Now we have data quality in place, we have a registry. Well, let's take a quick look just before handing over to Marius, what our virtual machine architecture looks like. So with this bare metal mixed node hybrid cluster structure, we have mixed nodes where some nodes are very GPU heavy, others focus more on CPU compute. On top of that, we host control plane, system tools, different amenities, as well as controllers. This spreads over a range of operating systems due to us getting operating systems from NVIDIA, such as BCM, the base command manager, or former Bright cluster manager, also DGX Ubuntu, and then Ubuntu for our own VMs in order to be as close to DGX Ubuntu as possible. When it comes to Kubernetes, this can be a combination of container runtime and kubeadmin, or for a more hosted platform, something like Rancher Kubernetes engine. When we want to do development in cloud, we can of course utilize something like AKS or EKS. And in fact, we have a dedicated team providing clusters as a service in Novo Nordisk called the Heimdall team that we can also sync up with. Then we add different amenities on top of our clusters to make them nice and easy to use. Things like Argo CD for continuous delivery through GitOps, things like the Harbor registry, cert manager, observability tools, etc. We are working with scientists who may be less familiar with Kubernetes, so we want to make sure it's as easy as possible for them to get started. Finally, hooking in storage mainly through AWS S3. That's both for the Harbor registry, but also for AI to ensure low latency data access for models. Here I will hand over to Marius to tell you more about Gefion.
Right. Thank you, Gustav, and congratulations to everyone. You made it to the chapter 3. It's 3:45. So I'm going to fry your brain for the last 15 minutes. So in this chapter, we're going to talk about infrastructure and tool. So we're going to start with giving you more details about the special hardware that we are going to work with in the future. And then later on, we're going to talk about our experience working with our GPU workloads. All right, so how many people in this room heard about Gefion? All right, okay, so please don't spoil the others. And then and for the one who didn't hear about it, please wake up because it's going to be fun. So Gefion is an AI supercomputer. And more precisely, what is stated here, NVIDIA DGX SuperPod. DGX stands for Deep GPU Accelerated. So it's basically an infrastructure specialized into LLM training or inferencing. So let's get a bit closer to the actual setup. So we're talking about more than 100 NVIDIA DGX H100. That sums up more than 1,000 actual NVIDIA H100 nodes, all interconnected with the next-gen networking hardware named NVIDIA Quantum 2 InfiniBand. A little bit of detail, each of those nodes come with an 8 tensor core and more than 600 gigabytes of RAM. So we're talking here about infrastructure meant to scale AI workloads, right? Yeah, I mean, I'm getting hot when I see such a sexy hardware. All right, so one of our first objectives in our team is building an inference cluster with the other SME subject matter expert. So on one side we have this hardware. I mean, this is not Gefion. We are going to have hardware close to Gefion. That's why it's H200 in this case. And then in this inference cluster there's going to be, of course, train model, because inference is like deployment of model, right? So we're going to have machine learning engineers that needs to access to the specific hardware. So it's quite far because we're talking about juicy hardware and everyone wants to get hands of it, right? And basically they won't just go in the data center and connect the laptop to have access to that. So this is where we come into play. And before getting in the how we tackle that challenge, I want to give you more specifics about the architecture that we have. I believe maybe some of you thought like H1 stands for heroin, but no, it's actually Hopper. Hopper is a scientist in the United States, and fun fact about NVIDIA, they like to name their architecture based on scientists. You have Ampere, Hopper, Gracewell, I don't remember. Anyway, that's not the point. Well, the Hopper architecture comes with three major features. The first one is security. So basically, whenever you have two GPUs communicating, you can add encryption on top of it. So that's very cool. The second one is multi-instance GPU. So it's a sharing strategies for GPU. We're going to dig a deep dive later on. It's very cool for whenever you have inference, you want to distribute your GPUs. And the last feature is scalable interconnects. It's just a very next-gen networking hardware that helps to scale. So if you have large training jobs that you need to do, you can easily scale thanks to this architecture. So it's very specific. So we're going to focus on the last two ones. I'm going to give you more details, actually, what it is. So I'll try to simplify the networking challenge that the Hopper architecture is trying to solve. Let's say you have two teams, two researching teams. They are very talented, very fast analyzing data. And they are sitting very far from each other, so they need to communicate to deliver new drugs, right? So they analyze the data, each of them, but to communicate, they have to go to a coordinator, and that coordinator only accepts pigeon to communicate. Sorry, he's living in the past, right? So we can see here that no matter how fast they are at analyzing data, there's going to be a bottleneck problem. So what if they could just communicate straight using SMS or whatever? I mean, they're not going to do SMS, right? But it's just an example here. That's basically what is at stake whenever we're talking about GPU to GPU, peer-to-peer GPU, or RDMA for the one who knows read access direct memories. Direct memories. And well, whenever you have GPUs in distributed environments, so I mean different nodes, whenever they have to communicate, here the example of the coordinator would be the PCI Express, which is the legacy system. It was it was quite fast, but not up to the quality that we want to do, so it was average of 60 gigabytes per second, whereas the next-gen hardware, NVLink, NVSwitch, that is connected to the GPU inside the node, and with the InfiniBand that allows to communicate from a GPU from one node to another one, start at 300 and can go up to 1,800 gigabytes of RAM. So yeah, sometimes I'm thinking about going there just to download my movies, but yeah, super fast. One use case, what is good about peer-to-peer, it's in one case of training, for instance, is good for molecular dynamic performances. So if you have to train model that helps to predict the movement of a molecule. So this is one of the use cases for the ones who are interested in that. The other challenge, what I said earlier on, was the MIG, the multi-instance GPU. So let's take again those two teams, but now they're sitting in the same building because management felt like it's better than SMS, right? But they got into a beef. They don't want to talk to each other anymore. So they're going to go and work each on the side, analyzing data. But this time they need an actual lab or workspace in the actual building to do the processing of the data to release new drugs. But if team 1 booked the shared workspace, that means team 2 is on hold, right? So what if the workspace has the capability to be breakdown into smaller ones, so each team can get allocated and isolated smaller rooms to do their work. So that's basically what is at stake here with a multi-instance GPU. So if you have, based on the architecture that you're working on, here, for instance, is A100 is not Hopper, it's Ampere. You can break down your GPU into what's called GPU slices. So you can do a mix of memory and compute, and then distribute it in an isolated environment on your stakeholders. So later on, they can use it efficiently. All right, now let's go back at our early objective, which was shortening the access to the GPU. So basically, we have many different types of nodes. So we're building a Kubernetes cluster in the middle. We're using Volcano. I think you heard a bit about it when Ricardo said about it today. So it's kind of the same as queues. And of course, we deploy the NVIDIA operator and what talked Gustav about early on, a Arbor proxy to host the large images containers. And before going into the subject, I would like to give you a little bit of preview what does what. So Volcano, as you said, is like queues. It's good at doing batch scheduling, whereas the NVIDIA operator is very good at managing the underlying hardware, GPUs. So yeah, it's an amazing operator, very complex. And then if you have different types of GPUs, if NVIDIA base, it's going to operate very good. And of course, it supports different type of features such as multi-instance GPUs, networking, and so on. But it's very complex when we talk about getting to understand what it does, because it works with different architecture, and it is it's a kind of a young project, I would say. So they're still developing it every day. It changed quite fast. Whereas Volcano, has said Ricardo earlier on, the community is in China, so it's very difficult to find documentation. And the ecosystem is not as much as updated, so yeah. So now let's get into the demo, right? And I hope that you will learn about a bit more about the NVIDIA operator. We're going to deploy a LLM in the cluster use GPUs, and then we're going to use some Volcano job to interact with that model. And then we're going to display everything in Argo workflows. And again, here, Gustav said, as he said, we are about running AI. Argo workflow in this case is just an experiment. It's not something that we are certain to go with. So yeah, this is just a demo in case everything failed. But let me go back to. I think you can see it all right. So here I took the liberty of preparing a small document. So I'm just going to run command after each other. So first I'm going to start by, I'm going to show you a bit the hardware. So the hardware is a heterogeneous one, like the one that we're supposed to work on-prem with what's going to be next to Giffion. So in this sense, we have 810 node pools. We have a normal CPU node pools, but we have 2 GPU nodes and 1 InfiniBand node for testing, networking, and benchmarking. And yeah, right now what I wanted to show is when we install the NVIDIA operator, how does it look like? So as you can see here, I didn't take the liberty when installing the NVIDIA operator to specifically install it in the nodes where there are GPUs, because you can configure to just install it in some node, because mostly it works with daemon set, because it's going to do what's called NFD, node feature discovery, to discover the hardware and so on. You're also going to install a Kubernetes device plugin to control the underlying driver. I'm going to speed up a bit, but basically, when you look at the nodes, it looks like this. It annotates all the nodes that it found. The 2 Ampere nodes are going to be annotated by the operator. And then after that, what I can show you is that we deployed Olama. It's open source Llama. It's just it's a Llama model, but open source will be deployed in cluster using MShot. And if you want to make sure that your model, that your application is using GPU, you have to do like this. You have to use container device interfaces. So request it this way, the same way that you'll do it with a CPU, but a bit different, right? So it looks like this, and now I'm going to create a job. So here I created one job, one workflow with Argo workflows, and that workflows encapsulate Volcano jobs. So I'm just going to list that right now. I get a bit lost in this. Sorry. Yeah. So I'm getting this. So let's see if it started. Oh no, it failed. Let's give it a second. I have to initiate it again. How are you on time? Okay, so we have this that is running right now. I'm just going to grab this, and it's a bit up. I think I should have done like this. Yeah, this is better. So I'm getting the job. I'm trying. I will export this to yeah, I think just put like this. And whenever I run this, I know that's creating another job. Oof, I'm a bit lost on this. Screen is very small. But anyway, what I wanted to show you is that here, what I'm doing basically on the pod that is running on the job is I'm triggering Olama to passing a question, like I'm just asking, what are the 3 benefits of attending the Kubernetes community days? And I'm writing it in the file because I want to use that file in other containers to pipe it, but I'm not going to show it because I'm a bit out of time. But if you look at the ingress, here, if I go to Argo Workflow, I think I have it open already. Yeah, here. So it looks a bit like this. So it's going to trigger a job, and then but the Argo Workflow is going to create some work. This is overall workflow, but with 3 different jobs that are just like hammering the LLM model. And whenever you're trying to get the output, you can just I'm just writing in the logs, so you can just list the logs and to see the output. So I can just do K logs, and I don't have auto completion in this one. $pod. Yeah, so basically you have the instance here because I'm asking 3 questions on each job. One, I'm asking 3 benefits, 2 benefits, 1 benefit. So it works a bit like this. And then I showed you already on Argo Workflow how it's running. So that's basically it for the demo. And I'm going to go back to the presentation. So what you saw earlier on from this current slide, what you saw earlier on is a kind of a static allocation, but we want to do dynamic one. So, I mean, if you have many workflows that you have to, many applications that you need to schedule on the GPU, to require GPU, you don't want to do it manually like this. There's something that's called DRA, Dynamic Resource Allocation. That is making sure that whenever you have a GPU, it can be shared between multiple workloads, but you can also scale it. So it makes things more dynamic. It's one of the latest features. And I'm going to not spend too much time because I think they were very good talk about what is batch scheduling in Kubernetes using queues. It's kind of the same concept in Volcano. You can have queues giving priorities for preemption, etc. And then I would say that one of the good features of what that comes with Volcano is that it's compatible to some ML frameworks such as TensorFlows, TensorFlow, etc. I'm not the ML expert, unfortunately, but it's compatible at some point. Now I'm going to talk about the chapter 4, the challenge and potential solutions. So one of the challenges that we have is like this whole thing is quite new for us, but we need to stay focused and help to actually contribute to drug discovery. And another challenge is that we're meant to work with machine learning engineers, and then whenever we accumulate both knowledges, we think about getting something awesome, Elon Musk, but at the end of the day, they are not platform engineers, so it's very much difficult for them. They don't care about pipeline, etc. They're math people. They are very focusing on some other aspect. But we still need to keep the expertise, so that's why that's what Gustav said earlier on. We're doing workshops with them, and if you remember the talks about the Lego last year and KubeCon Paris, what Marius said, like we need to stay focused on early values and earning. So our workshops are oriented around getting the values, and then of course we need to get close to them, but by trying to decomplexify stuff. But as I said, Mark yesterday. There's some balance that needs to be found because otherwise you end up doing too many layers. And now I'm going to give back to Gustav about the last chapter, future directions.
Thank you, Marius. Yes, just to take a final look into what a potential future could look like. We have this multi and hybrid setup with both multi-cloud, AWS and Azure as our 2 main clouds, but also we have inference on-premise cluster. So on top of that, it could be different batch schedulation mechanisms based on what Marius described. On top, adding the AI workloads such as PyTorch and TensorFlow you mentioned as well. So this is just a potential future, what it can look like for us. Then I want to say we also have a lot of focus on circular for zero, we call it, our carbon footprint, limiting CO2 emissions, etc. So based on previous lightning talk, when it comes to placement of our hardware and location and such, we might consider putting things in Sweden, of course. And then we are considering things like mechanical sympathy and all the way to how you structure your code to run more efficiently, of course, and just really minimize the CO2. But that's it, more or less. So I think we are ready to take any questions.
Yeah, thank you everyone.
Thank you so much, Marius and Gustav. Unfortunately, we're running out of time for questions, but thank you so much. They can find you later on, right?
Yes, absolutely.
Yeah.